I think a special requirement for being Vice Chancellor is to be able to leap up this enormous step, which I have to confess I can't do. So, good afternoon. I'm Paula Chadwick. I'm the head of the Department of Physics, and it's a great pleasure to welcome you all to this Ogden at 20 celebration on behalf of the Physics Department. You no doubt have noticed that we're on a strike day today. From the folks standing outside. Many of the people standing outside are doing so because they feel very strongly about the issues that are affecting university staff at the moment. They would much rather be here, I know, and they're making a real sacrifice for their cause. Physics is a big department. We've got some 250 teaching and research staff in various combinations, around 40 technical and support staff, and almost 200 postgraduate students. I was quite surprised to discover this myself this morning. Between us, we teach around 1,200 undergraduates. There are 7 research sections in the department: condensed matter physics, quantum light and matter, physics education and scholarship, the Centre for Advanced Instrumentation, the Centre for Extragalactic Astronomy, the Institute for Particle Physics Phenomenology, which for obvious reasons we normally call the IPPP, and the Institute for Computational Cosmology, also known as the ICC. The Ogden Centre for Fundamental Physics, 2 buildings, east and west, houses the IPPP and the ICC, as well as much of the Centres for Extragalactic Astronomy and Advanced Instrumentation, making that link that's so important between observation and theory and instrumentation. So much for all the statistics. So to my mind, this event has 3 purposes: to celebrate, to thank, and to explore. And we celebrate the achievements of the Ogden Centre over the last 20 years. These include world-leading theory support for the experiments at the Large Hadron Collider in their searches for new physics, and the creation of the most accurate and comprehensive simulation ever of our local universe, to pick out just 2. Some of this work has other, perhaps more surprising applications, such as pandemic modelling and improving cancer treatment. Every bit as important to celebrate as the research is all the science outreach that's been done over the last 20 years, particularly with schools in the northeast of England, some of which are among the most deprived in the country. The Ogden Centre truly comes alive when filled with the chatter of, frankly, slightly overexcited young people. Next, the thank you, a big thank you to all the supporters of the work of the IPPP and the ICC over the years, many of whom are here today. Thank you to each and every one of you, however you have supported the work of the Ogden Centre, and of course particularly to Sir Peter Ogden, without whom the Ogden Centre wouldn't exist. Now, Peter Ogden, with Carlos Frank and our much-missed friend and colleague James Stirling, was instrumental in posing the 5 key questions about the universe, which formed the basis of the Ogden Centre's work and the exploration part of this afternoon. What is the dark matter? How much is there? And where is it? What is the connection of neutrinos to matter-antimatter asymmetry? What is dark energy? When and where was it generated? Was Einstein right, specifically about gravity, but you could ask it about many things? And finally, how did planets originate, and what are the conditions for life? We have 5 excellent speakers lined up, most of whom are early career scientists who will consider each of these questions in turn. Carlos is the not-so-early career scientist. First, however, we will have an introduction to these questions and how we arrived at them from Professor Jim Peebles. So it's difficult to think of any key development in modern cosmology in which Jim Peebles has not played a central part, but he's best known for his fundamental theoretical work on the cosmic microwave background radiation. While he was still a student at Princeton in the mid-1960s, he made his first seminal contribution by predicting, together with Robert Dicke, that if the universe had begun with the Big Bang, then it should be permeated today by cold radiation, detectable as a background of microwaves, the echo of the Big Bang. Not long afterwards, this very radiation was discovered by Penzias and Wilson, who were awarded the Nobel Prize for their discovery. Remarkably, very soon after the discovery of the microwave background, Jim Peebles realized that this radiation would have retained an imprint of the small fluctuations that would later develop into galaxies and other structures that characterize the universe that we see today. This extraordinary foresight led to a 3-decade search for inhomogeneities in the microwave background radiation, which were eventually discovered with the COBE satellite in 1992. Subsequent measurement of the temperature fluctuations with much high sensitivity and resolution, with the WMAP and Planck satellites, match his detailed predictions with exquisite precision. This match has led to the acceptance of the inflationary cold dark matter model as the standard model of cosmology and the transformation of cosmology into a precision science. Along the way, he has been garlanded with many honours and awards, far too many to list, and in 2019, Jim Peebles was awarded the Nobel Prize for Physics for, as the committee put it, theoretical discoveries in physical cosmology, a short phrase for an enormous body of work. It's a great pleasure to have him with us today to share his insights. And please welcome Professor Jim Peebles.
First, do I need this? I guess I do. Is it on? So, it's a deep pleasure to be here to celebrate the Ogden Centre. Only recently have I become aware of the fact that I must pay attention to monetizable research. And I must learn to get along with the fact that I have spent my entire career entirely devoted to issues that have next to zero probability of being monetizable. But yet I insist that my work and what goes on in the Ogden Centre and through this great university on pure curiosity-driven research is essential, first, to allow applied research, and second, I think equally important, to inspire all of us with the spirit of inquiry about the wonderful world around us. So, I propose to talk about the issue, what do we mean by physical science? I will offer some opinions, then begin. Do I have it? No, wait, it was there. With this book by Bruno Latour, who I guess could best be called a philosopher, and Steve Woolgar, a sociologist of science. A fascinating experiment. Latour spent 2 years embedded in a center for the research of biological molecules. Latour had no experience in physical science. He didn't know the subject. He instead played the role of an anthropologist who observes the behavior of a society that has been very little affected by our society, and by observing that society, try to deduce what they're doing and why. He played the role of a sociologist looking at a community of natural scientists. Of course, he got some things right, and others perhaps more questionable. This is illustrated by the quotation I've drawn from this book. In the end, they're saying, we're not questioning whether these molecules are real, but we're insisting that they cannot jump out of the equipment that makes their existence real. It's a wonderfully nuanced notion of existence and reality. Another line of thought is expressed by Thomas Kuhn, who points out very correctly that we as physical scientists are influenced by our society. It's inevitable. We must be influenced by our society. We learn from it, we profit from it, and we contribute to it. that led him to the thought, well, can you really separate our theories from our society and the ideas that are built into the society that we must necessarily follow because we learn them from an early youth? It's a good question, which I will address, but first I point out yet another opinion by an American, we could call him a public figure, important in the development of psychology and natural science. He pointed out it is as if we were really made of ether, atoms, and electrons, but don't take it too seriously. That's one line of thought about science. James was friendly with a rather more eccentric person, Charles Saunders Peirce, who led a rather erratic, eccentric life. James kept trying to find him a good position because he realized the quality of Peirce. But Peirce was eccentric, but he did, I think, understand a deep point about the nature of research. He argued that we have three quite different ways to measure the speed of light. First off, machinery in those days was sophisticated enough that you could measure the speed of light in the laboratory, get a number. Astronomers could get a speed of light. For example, Jupiter has satellites that move around it. It's easy to see when those satellites move behind Jupiter. And you measure the time elapsed between a satellite completing an orbit around Jupiter and back to entering Jupiter again. That time varies as the planets move around the sun and the distance between Jupiter and Earth changes. So you knew the scale of the solar system because you start with surveyors who had measured the radius of the Earth, used trigonometry to get distances then to the planets. They had pretty good distances, and so you have a distance and you have a time delay as the distance changes, gives you the speed of light. That speed of light agrees with the laboratory measurements. That's kind of impressive. Also, people had played for many years with electricity and magnetism, and by this time people have seen that the two can be put together. That's Maxwell, although leading up to Maxwell, and already they were suspecting that the velocity that comes out of that theory is the speed of light. So you have three quite different means of measuring one quantity. You find that the results are consistent. Is that simply an accident? Surely not. Surely it means that the speed of light has an objective reality, independent of our culture or of our choice whether or not to measure it. A beautiful thought, and one that is really central to our existence. What is going on next? Well, okay. Now I come to James Clerk Maxwell. You can read his comment, very, very insightful. We often say that scientists in their old age tend to get complacent and wonder, well, after me, what can you do? Maxwell has been accused of this, but he didn't mean it. As you can read here, he has this beautiful notion, but rather poorly phrased, I think, that we are going to, where is it now? We have no right to think that there is nothing to be discovered. What wonderful things will be found, he said, as we pour knowledge into younger, bright people. The notion of pouring knowledge in is a little bit disconcerting to me, but he has the right idea. Isn't that right? The universe is a wonderful big place. There are lots of things to discover. Surely new generations with fresh minds will discover new things. And of course that has happened in abundance. Do I want anything else? Oh yes, we must next point out that electromagnetism is used all the time, from the design of power plants that convert mechanical energy into electromagnetic, to the transmission lines that send electromagnetic fields to substations that divide up the energy flow, put it into your home to turn on your lights, trickle down to your cell phone to cause electrons to move about in crystals, liquid and solid, to make radio signals that will communicate with cell towers, satellites. All of that, each of these applications is an application of Maxwell's equations, and it is therefore a test of Maxwell's equations. If Maxwell's equations were wrong, surely you wouldn't get all of these applications right by the use of Maxwell's equations. Wonderfully clear picture that Maxwell's equations are surely a good approximation to reality. But we know they're not exact, that if you apply Maxwell's equations to an atom, you get into real trouble. We needed a deeper theory, quantum electrodynamics. Quantum electrodynamics has as a limiting case Maxwell's equation. It goes deeper, it's subject to much more precise tests, then it passes them. Beautiful. But again, quantum electrodynamics is an approximation, a limiting case of electroweak symmetry, which we presume is a limiting case of a grand unified theory to be discovered. The point is simple, that we have excellently successful theories that pass lots of tests that surely mean that they're a useful approximation to reality, but an approximation, one that can be improved, but in fact, to be practical about it, can never reach a final theory because no experiment can be arbitrarily accurate, so we can never check that a theory is arbitrarily good. That's the nature of natural science. We can make persuasively good approximations to reality, but we'll never reach it. That's just the way it is. So I guess I've said all of this. Let's go on to, there it is. Maxwell's equations are wrong, but yet they're wonderfully useful, a good approximation. So it is with all of our physical science. And let's go on now to an application of these methods and thoughts in philosophy to the expanding universe. This is a cartoon from based on an essay written by the Dutch astronomer Willem de Sitter on the occasion of the notion finally accepted that maybe our universe is expanding. Can I use a pointer to go on to this? Yes, I can. Do we see it? No, we don't. You don't see its pointer, do you? All right. First off, Einstein had postulated out of the blue that a sensibly built universe would be uniform, the same everywhere. That was a philosophical notion.
You can use a laser if you want.
I can use a laser.
Point at the screens.
But I can't point at the screen because it's right. Never mind.
You might be able to. Maybe not, I don't know.
Okay, here is Einstein's universe. He had no reason to argue that this is a sensible universe. None of the data that support that universe was available yet, but he guessed it, and it was so elegant, and elegance is really influential to us, that this is the way a sensible universe would be. You notice that, of course, we must think of beings who live in two dimensions. You must not ask, what are people doing off the surface of the balloon? No, you live on the surface of the balloon. You can move in two directions. Get used to it. You notice in particular that if the balloon is not expanding, then you can go in one straight direction and get back to where you were. Wonderful. It's a finite universe that is the same everywhere. Notice, though, that de Sitter, the figure you see in caricature, first there's a lambda, which we'll get to, written backwards, artistic license, blowing into the balloon to cause it to expand. First off, you must understand, you and I are not expanding, apart from the usual biological effects. Our galaxy is not expanding, apart from, perhaps material being blown away in explosions. The expansion of the universe has nothing to do with you and me, apart from the fact that it means our universe that is so beautiful is not forever. But rather, the distance between galaxies is increasing. And although if I had let's see, can I Oh, yeah, I guess I can. Suppose you live on this galaxy. You see this one moving away from you, you see this one moving away from you, you see this one moving away from you. You are entitled to say, wow, the universe is expanding and it's expanding away from me. But of course, any other observer on another galaxy would see the same thing. This is universal expansion. Notice also that if you are on this galaxy, you see this one moving away from you. This one is about twice as far away. It's going to move twice as fast because this one is moving away from them, this one is moving away from this one. So the rate at which galaxies move away from us ought to be directly proportional to how far away they are. That theory was first found by Edwin Hubble. Others had guessed at it in 1929. Here's Hubble's data. And it might not be very impressive looking, and I don't think it was, but it's again part of sociology. People were really impressed by that apparently linear relation. Here are data that Hubble and Humason, his assistant, obtained in the 1930s. You notice that the recession velocity is up here to the left, kilometers per second, 4.5 log base 10. That's 4/10 to the fourth centimeter kilometers per second, which is to say a tenth of the velocity of light. I was 1 year old when this was published, and they had already reached 10% of the speed of light. Wow. It shows how advances can become rapid or very slow to get this in a rather different scale, but the general idea, to get up to recession velocities near the speed of light took another half century. Advances are either fast or slow. It just depends on what can be done. Now again, mentioned the universe, we have good evidence now, started out dense because it's expanding and hot when it started expanding. A high temperature dense universe will relax to statistical equilibrium, thermal equilibrium. That means there will be a sea of thermal radiation. You recall that thermal radiation has the property that you tell me the temperature, I'll tell you the intensity of that radiation at each wavelength. A great advance in quantum physics already more than 100 years ago, 125 years ago or so. And it's illustrated here. Give me the temperature, I'll tell you the intensity at every wavelength. Well, we could spend a lot of time discussing how that was done, but the measurements were made. They're very difficult. It took two groups, each of them more than 15 years, to accomplish this measurement. As it happened, the two measurements were completed within a few months of each other. A small salutary point to mention. These two experiments were done independently. They got the result after 15 years or so of labor within months of each other. One of these experiments yielded a Nobel Prize, well deserved, to John Mather. The other experiment, run by Herb Gush at the University of Manitoba, wishful thinking, the University of British Columbia in Western Canada. Either result, as you see, proves the point. This is thermal radiation. The fact that two people got it independently, wonderful confirmation, but one of them would be convincing. One of them won a Nobel Prize. The other received the respect of his colleagues and on to something else. That's life. So we have a hot universe. We're convinced it's hot and cooling down because it's expanding, and this radiation is thermal. You can't account for that thermal property unless you accept that our universe is not forever, that it has evolved from a very different state. That's a deep advance, and yet it looks pretty convincing. We also have evidence that the universe is clumpy on relatively small scales. Here is a map of the distributions of galaxies across the sky. You see it's lumpy. On average, it's uniform, but there are distinct lumps. Down below is a map of a section of the sky, temperature in the microwave background. This temperature fluctuation is a part in 10 to the fifth, a few parts in 10 to the fifth. It's tiny. A puzzle that was deeply disturbing in the early 1980s was how did it happen that the matter distribution got so clumpy when the radiation distribution stayed so smooth? Because you would have thought that in the early universe, when temperatures were high and the matter was ionized, then the radiation would strongly interact with free electrons because they can scatter off each other. The free electrons scatter off the ions. The result is that the mixture behaves as a fluid. If you move part of the mixture, the baryons, in order to make galaxies, you're going to move the radiation too. And that's clearly didn't happen. What in the world could that mean? In 1982, I introduced the notion. Where are we? Oh, I guess I should turn the page. Oh, there it is. Actually, historically interesting that in 1980, what is it? Early 1982, there was a suggestion that maybe the radiation isn't so smooth after all. I had to pay attention to that preliminary indication because one of the groups that found it is based at Princeton University. I was there watching them get the data, so I invented a theory that I published in early 1982. I think it's a beautiful theory, but it's wrong because my colleagues withdrew their claim of a detection and put a much lower bound on how irregular the microwave background could be distributed. That led me, as a good theorist, to invent a new resolution. You have a problem, you invent a theory. So I invented a theory. It required the postulate that most of the matter in our universe is not baryonic. It's not the stuff you and I are made of. That most of the matter in the universe is dark, doesn't interact with radiation matter. That was a purely ad hoc assumption made to save the theory, right? And that's legal, but of course you have to recognize that it is an assumption until you have evidence for or against the notion. And I had to do another thing to account for the growing observations. 2 years later, in 1984, I had to say, let's look at this cosmological constant, that lambda, that Einstein had introduced. This cosmological constant Einstein had introduced for a very special purpose. By the way, I think I have, yes, here it is, the hated cosmological constant. Einstein put it in because he noticed that his uniform universe could not be stable. If you have the matter in the universe more or less smoothly distributed, you let it go, it'll collapse through gravity. That's no good, Einstein said. Our universe is forever, of course. So he put in a new term, that lambda term, here, so as to balance the universe. It has the effect of pushing things apart, and so he has things in nice balance. Gravity pulls, lambda pushes, and they're in equilibrium. Of course, you recognize that that's an unstable equilibrium. It's just not acceptable. The slightest touch, if you make the universe a little smaller, then gravity will dominate, the pull of gravity will dominate the repulsion of lambda, and the universe will collapse to a big crunch. That's no good, Einstein said. If, on the other hand, you expand the universe a bit, then the push of lambda will exceed the pull of gravity, and it'll expand. In this essay written by De Sitter, he asks the question, why is the universe expanding or blowing up? The answer is the push of lambda. Another answer cannot be given. So in 1930, the accepted notion is that the universe started out as Einstein's static universe and then started expanding because it's slightly unstable. And once lambda gets hold, it will accelerate away. The universe will expand with ever increasing speed. Einstein pretty quickly realized that if the universe is expanding, then he has no longer a reason for that lambda, and he wants to get rid of it. it's really worth pausing now to consider the thinking of Einstein on this point. Here, in the years just following the Second World War, the Belgian physicist and priest Georges Lemaitre had decided that, there is something in this lambda. He wrote a letter to Einstein arguing for this point. Einstein courteously wrote back, here it is, "Dear Professor Lemaitre," and if you can find it somewhere down below, he points out, your arguments, there exists a reason to try bold extrapolations and hypotheses to avoid contradiction with facts. Maybe you're right. But we noticed that, in fact, Einstein was just being polite, because a little later on in this letter, Einstein is writing, forgive me while I so I can read. "Since I have introduced this term, I had always a bad conscience. I cannot help to feel it strongly, and I'm unable to believe that such an ugly thing should be realized in nature. That is what has come to be called the dark energy." I believe that Einstein's argument was entirely sensible and reasonable. If I had been around at the time, I would have said, "Yes, you're right, Albert." But of course, nature decides, and nature has decided that this lambda has to be present. So have I said all this? I'm tired of screening up, so I'm going to come over here. I come now to the years around 1990. An interesting situation was developing. First, many people were convinced that lambda should be 0 because, after all, it's ugly. People were also pretty well convinced the universe has to have no space curvature, because if it had space curvature, two bad things would happen. First, we would be living at a special epoch, because the curvature of space-time, of the space sections at constant time, would have to be relatively small, or else we would have noticed it already. So we would have to have flourished at a special time, just when the effect of space curvature was becoming observable. That's kind of ugly. So surely space curvature is negligible, lambda is unimportant, and so the universe is of a special sort. Einstein decided they called it scale invariant beautiful. That's an elegant universe. It's the one you and I would have chosen, given the chance. At the same time, the evidence developing was that the mass density of the universe is well below Einstein de Sitter. And second, that we have to do something about it. And so there were those of us who felt you're going to have to learn to live with lambda. I used to enjoy in those occasions giving colloquia with the title, Learning to Live with Lambda, which I thought was very clever. And it was fun also that many of the younger people got annoyed at me for arguing this way. It's really silly to think the universe is not Einstein de Sitter. But, we came to live with it. So what do we have next? Does this go forward? Yes, it does. We started making measurements of mass density. One way to measure masses of galaxies is to look at the effect on the motions of neighboring galaxies as they move around relative to the masses of other galaxies. The first statistical analysis of this was done with my former student, Margaret Geller, 1973, a time when a lot was going on. And we needed motions, and we had a treasured 226 galaxies with measured relative velocities. That's velocities measured by Dopplership. 226. In one measurement these days, they get several tens of times that many measurements. But we were able to see, first, that the mass of a galaxy seems a lot larger than is expected from the masses of the stars you see. It was the first hint of dark matter. Second, it didn't look as though there was enough dark matter to make an Einstein de Sitter universe. So, when I paused to notice, The Soviet Union was at that time, of course, a very repressive place, but physicists had a special niche that allowed them to be bold because Stalin and then Khrushchev wanted atomic bombs. And so they were able to make adventurous ideas because they were free to speculate more than, say, a biologist who had to follow the line of Lysenko. Through that fortunate fact, these people, including Zeldovich here, Yakov Zeldovich, were making great inroads in cosmology, following a path very close to what I was doing in the US. But there was one big difference. It was known then that the oldest stars had low heavy element abundances. It seemed clear the stars make the heavy elements, so younger stars made up of material that's already been polluted by older stars have a higher heavy element abundance. Young stars, low heavy element abundances. Young stars, did I say it right? Young stars, lots of heavy elements, relatively speaking. Zeldovich saw the same was true with helium. And helium, George Gamow had already shown, would be produced in abundance in a hot Big Bang. If Zeldovich had had a chance to talk to a few astronomers outside the Soviet Union, he would have quickly learned that there was a deep puzzle. Why is there so much helium in the old stars? It was a real puzzle. If Zeldovich had known that, he would have known that the hot Big Bang is not contradicted by helium abundance measurements, that in fact the helium abundance is pointing to a hot Big Bang. He could not have that conversation, of course, because he had played an important role in the development of the atomic bomb and the hydrogen bomb. He knew too much for the Soviet authorities to let him go outside the country and speak to anyone. It's the effect, I think, you see, of a repressive society. Great things can be done in a repressive society. Consider the Soviet Army hockey team. Spectacular. Because they were allowed to compete and they wouldn't carry away any state secrets. But you couldn't do that to biology. Agriculture was suffering heavily because they weren't allowed to recognize the importance of genetics. Well, let's go on. Again, a chance interaction. Jerry Oestreicher at Princeton University and me got together, and Jerry raised a question. Can a galaxy that is supported by rotation last any length of time? He was aware that stars can't rotate too rapidly. If you do, they fall apart. They won't stay as rapidly rotating stars. They'll fission into pairs of stars or multiples. He asked if the same is true of a galaxy, a disk spiral galaxy. The answer we clearly showed is no. A galaxy in which the matter is all in the disk cannot survive. What's the remedy? Well, of course, you introduce something ad hoc to make it work. The remedy clearly is don't put the mass in the disk, put it in a bulge, a halo around the galaxy, because that is a stable situation. The notion again of dark matter. Here is Jerry Oestreicher, slightly older, with a galaxy, a spiral galaxy, whoops. And here is Amos Yehiel with his mother, and a paper, 1974. Put together all the evidence you had about masses, including the masses in halos of galaxies, and you conclude that the universe cannot be expanding at escape speed. That would be the speed of expansion if the universe were Einstein considered. The mass density has to be well below that allowed by expansion at escape velocity. We came up with an answer around 0.2 times the critical mass for expansion at escape velocity. A low mass density meant either that space curvature is present or else that lambda is present. It was a situation that many people didn't like, but here Mark Davis and I, a few years later, had a much better market decided that we got to have wholesale measurements of radial velocities of galaxies so we can make good statistics rather than the very crude approximations Margaret Geller and I had to live with. So he made the first really good approximation to a fair sample of recession velocities of galaxies. The departures of those regular recession velocities from what you would expect with uniform expansion was a measure of mass. Masses and counts of galaxies give you mass densities. And again, whoops. One problem with this thing, and I never know what to push. Where are we? It's about 0.2%. Mass density is about 0.2 times what you would expect if the universe were expanding at the Einstein de Sitter rate. Mass density is too low. You need either accept lambda, accept space curvature, or accept that Einstein's equation is wrong. And what was the easiest thing to accept? Well, that the cosmological constant is present. At the same time, people were pursuing measurements of the recession velocity as a function of distance from us. And that measurement, which had been a dream of cosmologists since the 1930s, was at last accomplished by two groups, Adam Rees and colleagues, Saul Perlmutter's and colleagues, around the turn of the century. This work was so brilliantly done that it earned these people a Nobel Prize in physics, and it also provided strong evidence that the line for Einstein de Sitter is clearly not fitting the data. This is pretty interesting, although I don't know whether if we had this alone, it would have convinced us all that the universe is not Einstein de Sitter. Anyway, we have another line of argument that goes as follows. We all remember resonance and its effects. For example, I offer this sophisticated scientific experiment. Why a definite tone? It's set by the length from here to here. As the wave goes in, bounces back, and either reinforces or not the wave motion. Resonance, an effect of boundary conditions. Notice here I have a shorter bulb, 5 minutes. Well, I'm going to shorten the experiment. Isn't that marvelous? It always turns out the same, and I'm always pleased that it works. In our expanding universe, we have an effect of boundary condition that produces just this effect. The early universe, as I said, is hot. Being hot, it frees the electrons from the ions. Electrons scatter off radiation. Ions scatter electrons. The result is radiation, ions, and electrons act as a fluid. If the fluid is not exactly homogeneous, it will be a sound wave. So the universe, now in time rather than space, has an oscillation. The oscillation is cut off when the temperature drops to 1,000 degrees Kelvin. The electrons attach themselves to the atoms. Atoms are freed from radiation, and so the oscillation stops. And so you will have this particular case that some wavelengths of departures from uniformity are favored, others suppressed. It is acoustic oscillations. This was a subject that was well and thoroughly discussed in the 1960s. It was about where am I? Oh, here. Yeah. Somehow I got these slides mixed up, I think. Let me come down to the front again. Good. Here in the year 1970, Jerry Yu, my first graduate student, with my acquaintance, my colleague, David Wilkinson and Bob Dickey, are at a meeting. Jerry Yu and I computed the effect of this resonance oscillations as the universe evolves and cools. This is an illustration of what happens. This is already in it's already 1968, but a good approximation. This particular wavelength oscillates until decoupling, and then it's free to go away, to expand. Of course, if you change the wavelength slightly, it'll end up going down when it's decoupled from the radiation. And in between, there must be a wavelength in which you don't get any amplification at all. And so you have this sort of distribution as a function of wavelength. That was predicted, computed in the way it should be in 1970. It took 30 years. I don't know why that's there. It's out of order. It was first detected in, it says here, the year 2000, roughly. So that's 30 years. Who knew? We had the effect, it's predicted, but 30 years later, it was found. Sometimes these things happen. First found here. It's pretty crude, but nonetheless, it's clear there's an oscillation in there. And here, again, it was, I think, quite independently discovered by Dan Eisenstein. He didn't know the earlier history, but he saw the physics, realized that if you take a Fourier transform of the power spectrum, you get the autocorrelation function. When a Fourier transform of a series of bumps is a delta function, Fourier transform of a sine wave is a delta function, you expect a bump, and there it is. It's really there, and the wavelength and so on depend on the cosmological parameters. And one other point that is well worth mentioning while we're at it, you compare our prediction back in 1970, we have zeros because there are some wavelengths that just don't get amplified, they pass through zero. That isn't what's observed. Why the difference? It's because of the dark matter. Dark matter doesn't interact with radiation and ordinary matter, so that part of the mass distribution doesn't receive the oscillations of the plasma fluid. That means that we expect far lower amplitude of oscillation because most of the matter is dark, not interacting. Therefore, you see another piece of evidence for the presence of dark matter. So important, multiple checks. Just as the speed of sound, well, I'll stop slowly and remind myself what else I wanted to say. Yeah, I said that, and I said this. Very briefly, you will hear talk of tensions. For example, what is the example? There. For example, one has a measure of the mass density in baryons. First at very high redshift, because at redshifts around 10 to the 9th, 10 to the 12th, 10 to the 10th, thermonuclear reactions are causing protons and neutrons to fuse to make deuterons that can, by particle exchange reaction, make helium. From the observed helium abundance in old stars, the helium abundance that Zeldovich wasn't aware of, you have an estimate of the baryon mass density that must be present to account for the observed abundance of the light isotopes of the baryonic elements. You have another measure from this pattern of oscillations in the distribution of matter and radiation. You have another measure from fast radio bursts that propagate through space between galaxies and pass through plasma, which causes longer wavelength radiation to arrive later. You have also cluster baryon mass fractions. The main point is just what Peirce said a century ago. You can measure the mass density in baryons in many different ways. We're getting closely the same answer. That's really impressive. That's such different phenomena. can indicate a baryon mass density that is so similar. It's as if the baryon density was a real quantity that had significance outside of whether or not we decide to measure it. And what else did I want to say? Oh, I should stop here. And thank you for your attention.
Thank you for an absolutely fascinating overview. I think we have time for one or two questions, if you're willing.
Okay.
Is there a quick question or two? We've even got a microphone wangler, I think, in the shape. No, I guess everyone's too shy. Maybe they'll talk to you. Ah, right. Oh, hey, look. How quick are you getting upstairs? You need to wait for the mic, because otherwise you won't be heard on the broadcast. Yep. Don't forget to switch it on. Two stairs at a time, brilliant.
So I'm not quite sure if it's a quick question, but if the universe is expanding, what do you think it's expanding into?
Oh. Remember I told you when you were thinking of the balloon analogy, don't ask what's outside the surface of the balloon. You live on the surface of the balloon. Now you could say, well, I don't really think I'm living on the surface of the balloon, and therefore the balloon is expanding into outer space. But of course, to follow the analogy, you mustn't think that. Fair enough. And similarly, we may say that our universe that we can live in is the surface of a hyperballoon with 4 spatial dimensions and 1 time dimension. But you mustn't really think that there's anything outside the surface of that hyperballoon. Similarly, you mustn't really think about what's outside our universe. Our universe is what there is. And so it is not meaningful to say what's outside our universe. Is that fair? Good.
Thanks very much. Let's thank...